So first of all, thanks you for coming here. I know that all the other talks at the same time are also really good, and also that it's 3:30 at the last day of a conference that was absolutely packed with good information, like my brain is about to blow up. So thank you all for attending this one. If you want to start the QR code right now, ahead of time, and just give me fives, it is going to be a good talk. Okay, so a bit about me. I'm actually relatively new to Postgres. I've been working on Postgres for the last 3 years. Before that, I worked on all kinds of different data systems, and I do apply a lot of ideas from other data systems in Postgres. In general, I like talking and sharing my knowledge. Because I'm relatively new to Postgres, I want to point out that I'm not sharing just my work and my knowledge. In fact, I've probably contributed less than 2% of the work I'm showing here. Nile has a bunch of amazing Postgres contributors and great engineers, and this is work of an entire team over 2 years. So at Nile, we are basically thinking about multi-tenant architectures and how Postgres can be a better fit for multi-tenant applications. So I'm going to start by talking a bit about those applications so you'll know what kind of problems I'm trying to solve. And then I'll show our architecture. But it looks like I'm going to show our architecture and then I'll go through step-by-step flows. This is, in fact, not what I'm going to do. I'm going to show part of our architecture, show how it's used in flows, show another part, show a few more flows. The reason is that I found out in test runs that if I show the entire architecture, by the time I get to flows, you forget which parts of the architectures it actually talks about. So don't wait for the slide that says, now we're talking about flows. It will never come. At the end, I'll talk about some things that if they only existed in Postgres, our life would have been way easier. I was a bit hesitant in that slide because Postgres is generally a very general system. It's supposed to solve all kinds of database problems for all people, every use case, while multi-tenant applications are only one use case. So maybe I shouldn't ask for too much things that are specific to us. But just talking to people around this conference, I discovered that actually multi-tenant applications are extremely common. I keep running into people who have built them. So maybe some of those suggestions are going to be more widely applicable than just me. If you want to follow along, you can point your phone and get a PDF of this talk. It will look like a random Google Drive. I promise you that it's my Google Drive, and all you're going to get is a PDF. Someone here, Florent, I think, someone told me that you can put viruses in a PDF, so I shouldn't be that trusting of something just because it's a PDF. My PDF, I promise, has no viruses in it. Okay, so what do I mean by rethinking about Postgres for multi-tenant applications? First of all, what are those multi-tenant applications? Basically, anytime you have an application that serves a lot of customers on the same application stack, we think about it as multi-tenant application. And hopefully you recognize at least some of those logos. I try to pick biggest and most popular examples out there. There are obviously hundreds of thousands, millions of those types of applications out there. And it's not new. Some of those have been around for a very, very long time, decades. So it's always surprising to me that designing these, operating these, scaling these is still considered a hard problem. Every once in a while, someone shows up and writes a blog post, how we sharded Figma, how we sharded Notion, how we sharded something. It's something that is still hard to evolve. How do people do it in general? There are two common models and then a hybrid of both of them. One model is commonly called isolated. You give a database or sometimes a schema for every one of your tenants. It has a lot of benefits. Those tenants are isolated. If you can put them on different continents if you need to. You have a lot of flexibility. If one tenant asks you for a backup, for a restore, for slightly different indexing, whatever, you can always do that. The problem is that if you have a lot of them, managing tons and tons of databases requires a lot of operational overhead. Usually, it also requires just large machines to run them on. You need to leave a bunch of headroom, so you have overhead from that. And if someone just spikes up and down in usage, it can be harder to deal with because you need even more overhead. It's already getting expensive. The other hand is what is known as the pool model. Happened to me far more popular. You basically dump all your customers into one schema, one set of tables, and try to manage them that way. The pros and cons are flipped. It is very cheap, relatively easy to operate. You can even run a bunch of reports across all your tenants, and this is very straightforward. On the other hand, hard to achieve predictable latency, very hard to scale out because you have to start figuring out sharding, usually when you're already a bit close to the limit. And a lot of stuff, if you need to do something per customer, you have one customer who has performance issues. You have one customer who could benefit from specific tuning. It gets really difficult. So I'm going to talk a lot about scale out. So it raises the question, do you ever need to really scale out? And there was a good talk from Leticia. She is like, oh, we have those amazing 768 thread AMDs. Maybe, does anyone even need to scale out in these situations? And the answer is that Postgres has bottlenecks that the size of the machine doesn't completely help with. Some of them are going to be worked on. We've seen a great talk about how vacuum will keep improving and get more parallelism. So there is definitely hope in the future. And there is also number of connections is a problem because you have processes, but maybe at some point will be on a thread model. The point is that you can hit a wall even if there is plenty of spare CPU, and even if you have plenty of spare memory. At some sizes, the management of the shared buffer pool itself becomes somewhat inefficient. And of course, if you need to actually go to other geographies, it doesn't matter exactly how big or small your workload is. If you have to be in Europe, you have to be in Europe. There is not that much choice about it. The thing about scaling out relational databases is that, well, they're relational. It means that you have tables and they relate to each other. Queries typically touch a lot of those tables, so you cannot really naively move things to different machines and different databases, because if you run a query and it has to touch a bunch of databases, you are not actually making your system any more scalable and any more performant. You have to the key to sharding is that you want a shared nothing system, and the point is that you want it. Share nothing means that you don't share things. You want queries to mostly be localized on a single machine to avoid this overhead. I had an entire slide explaining all the problems that can happen when you try to do it, and then I was like, nobody will actually want to do it, so why waste time on another slide? Now, if you look at one of those multi-tenant applications, you'll see that 90 to 99% of them have a where clause that says where tenant ID equals X, meaning that this, no matter how complicated the query is, and I try to make it as complicated as I could, you are not going to touch data that does not belong to tenant X. So if we manage to shard it in a way that all the data for tenant X is in the same place, we have pretty much won. We have data locality, and we can scale out by adding more and more of those. We took the idea a step further, and we said, what if we teach Postgres about tenants in all the layers? In the query layer, in memory, on storage, on disk, like just see how far we can really take this idea. And this is basically what I'm going to talk about, how far we went to this idea. One of the things is that we did it in our own extension, mostly, and we haven't talked about it a lot outside our own team. So while we have really smart people, there is always the nagging suspicion that this is pretty complicated. Did we miss an easy way to do what we did? So I talked to a lot of people at the conference. I'm slightly more confident that we didn't overkill it, that it really is hard, complicated problem. But if anyone is like, oh, actually there is a simple solution, I'm actually half looking forward to hear that. So this is not actually any physical architecture, it's more of the logical idea, is that basically we isolate tenants, so we create this virtual database for each tenant that looks like a real database, but it really isn't. And then we can spread them across different Postgres instances and different machines. For that matter, Postgres instance 2 could be in Europe. It's we try to isolate them as much as possible. And when we built the architecture that allows this general view, we had several, you know how when you do an architecture, there's usually you have a lot of requirements, but some of them have oversized impact on what the architecture actually ends up being. Like the combination or those specific requirements are just so challenging that they end up shaping everything. They eliminate a lot of alternatives and options. So those were the ones that shaped our architecture. We wanted complete data isolation. That was the key. We wanted to make sure that memory, disk, the data you'll never have a data block that has data from 2 tenants. We wanted single tenant performance to be identical as if this tenant was alone on the database. We didn't want anything to be even slightly slower just because there are other people on that database. But we also wanted to allow cross-tenant queries, meaning that if I have a to-dos table and it has 5,000 tenants, I should be able to query each of those tenants, but I should also be able to do select count star from to-dos where group by tenant ID having something. So those kind of reporting should be possible. They're not going to be fast, but they should be possible. There's a difference. We also wanted to allow tenant movement. So if a tenant gets large or noisy on one machine, we wanted to be able to move it to a different server. That was pretty difficult. We have a few slides just on that. And lastly, we wanted to support 1 million tenants. Spoiler alert, we believe this architecture allows up to 16 million. And I'll explain how and the math around it toward the end of the talk. Now, looking more in actual architecture, we have a bunch of components. So Nile Gateway is a proxy. And then we have a transaction coordinator for things that have to be coordinated across all the machines. We have metadata store for things like who is placed where and a lot of extra other metadata. And then we have those machines those are the serverless compute and the provision compute, those are the Postgreses. Under that, we added a storage layer that we have a page servers, which is mostly cache. The data itself is stored on an object store. Right now, it is mostly S3. If we zoom in on one of those serverless computes, like a Postgres, within it, the way we isolated tenants is that on every table, we gave every tenant their own partitions, and we placed them on table spaces. Why did we do both of those? Separate by partition is the main thing that makes sense in order to get the data separation in memory and on disk. It had a lot of drawbacks. I'll talk a lot about how we went around those drawbacks, but it did allow us to use all the work that was put into Postgres Query Planner, Postgres Vacuum. Any alternatives that had us not use partitions basically meant we have to rewrite large parts of Postgres from scratch. So we went with partitions for all the drawbacks that still seemed like the better of the alternatives. And then the table space. The reason we wanted this is that, remember, we wanted to take each tenant down to a separate storage layer. And table spaces is the main identifier that you have when you create something in database and gets taken all the way down to the storage layer. Once you're in the storage manager layer, you don't have the OIDs for partitions anymore. So we depend a lot on the table space ID. Now, we had to basically plug in our own storage manager. I'm going to talk a tiny bit about how we did that in a second. And then below the storage manager, the things that we plugged in as our actual storage instead of magnetic disks is something called SlateDB. If you are familiar with RocksDB, then SlateDB is RocksDB written to use S3 as storage, so kind of more cloud-native RocksDB. It's a fairly new project. It's started about 9 months ago. Nile is one of the companies that contribute to it quite heavily. So, adding our own storage. We basically used a set of patches that Neon, the other serverless Postgres company, have posted to the hacker mailing list about 2 years ago and were kind of abandoned about 7 months ago. We thought they were pretty good. I'm still not sure why they kind of got abandoned and why they were kind of left there for so long. But what it does is basically allow extension to implement their own storage manager and their own storage layer. So we use them. And then we needed a bit more stuff. We needed an API to know when table spaces get created, because this is where we create our SlateDB stores. We had a bunch of bugs around SMGR writes that were fixed in later versions, but we're still on Postgres 15. Hopefully, this will change by the time Postgres 18 is out. And then we added OID for create table space, so we can specify our own OIDs. We like UUIDs. We added them to the catalog. We introduced a new option for create table-like. I'll talk about it in a second. And we also made sure that when you inherit, if you have a table and then you create indexes on it, they actually get created by default on the same table space. I'm not 100% sure why this is not the normal default behavior of Postgres. Okay, with this part of the architecture in mind, let's talk about what happens when we create a tenant. So, can you see anything? It's a lot darker than what I thought. The flow starts when someone does insert into tenants, essentially. We have our proxy. It recognizes this type of queries. We intercept them, and we decide where to place them. If you didn't specify where you want the tenant, we will basically pick something at random. We don't have a very smart algorithm, because at this point, we know absolutely nothing about the tenant. Is it going to be big, small? No idea. Next thing we do is, after we decided where to place it, is create a metadata record. It has a tenant ID. It has the database where we decide to place it. It also has the table space ID. It's get generated at this point in time. Now that we know all that and persisted all that, we create a table space. Note that the fact that create table space is not transactional and cannot be part of a transaction is the main reason that we do all of it in the gateway. We have our extension and we have a transaction manager. The extension doesn't know about the metadata store. The transaction manager knows about the metadata store, but all it does is coordinate transactions. It could have been a transaction, except that it really couldn't, because we need to create the table space. Absolutely no idea why Postgres create table space is not transactional. Someone mentions that because it does stuff on disk, but I think that create table also does stuff on disk, so I'm really not 100% sure about it. Next thing is that we actually do the insert. Finally, the insert that got sent to us finally executes. The tenants table happened to have a trigger. The trigger calls a function in our extension, which goes over each and every table in the schema, triggered, and adds a partition to it. Once the partitions are added, we can return tenants has been created successfully and go back. How do we add partitions? We create a new table, very similar to the big partition table, but we also include physical layout. What does include physical layout do? This is something we added in one of our patches. It means that if there was a column that got dropped, the original will still have a placeholder, And the new table is also going to maintain this placeholder. Without it, the catalog entries are actually going to be different. It's actually fine. Postgres will support it. You can attach a partition with this difference. But it means that when we start moving tenants around, we actually have to track which columns existed in which version of the table. It gets very difficult for us to track those things. So we decided to just make sure that every dropped column remains in memory forever. After we did all that, we attach this table as a partition to the original partition table. Attaching partitions is by far the best thing to have happened to Postgres. If you have data to load like in big batches to a table, this is absolutely amazing. You can do all the loading in the background without disturbing anyone, no locks, no anything. Doesn't interfere with any workload. And then when you attach it, it basically doesn't take any kind of interfering lock. If you actually do alter table add partition, it takes a short but an exclusive shared lock. It can be disruptive. This is by far the best thing to have ever happened. Okay, we created a tenant. Presumably it inserted some data. We want to query data for the tenant. Yeah, I don't think anyone can read it. We introduced a GAC config. You can do set Nile.tenantID. You give it the tenant ID, and then you run a query like select star from tenants. You don't need a workload. In fact, a workload may be a bit detrimental. And we want it to run as if you're connected to a database that only ever contains this tenant. So again, our gateway intercepts that. Now it knows exactly what tenant you want to talk to, routes it to the database that actually contains this tenant, and then our extension intercepts it. An extension that is called Nile DDL, even though this today is completely misnamed. It says, okay, this is the tenant. It says select star from to-do, but I know which partition this tenant is in. So it hooks in the planner, slightly in the step after rewrite analyze, because they don't let us hook before rewrite analyze, otherwise we would do that. And we basically switch the OID from the OID of the table to the OID of the partition, and we continue running this query. This is fantastic for performance. It means that we don't have any of the planner overhead of dealing with what can be a very large list of partitions. No partition pruning ever has to happen. We do not need the row-level security either, so we also lose the overhead of that. We only query the subtable that has the data that we know the user needs. Performance cannot get any better than this. This is wonderful. If you need to do a DML, like an insert, basically the same thing, except that because inserts actually specify the ID by default, we actually can we grab the value for tenant ID out of the query when you do a bind, or if it's a simple query directly from the query, and we use that for routing. So you don't even have to do the setting the GUC. Okay, now we know all that. The step that is left is what if I want to do cross-tenant queries? And for that, we have to look into a part of the architecture that I haven't shown before, and honestly, I'm slightly afraid to show now. Previously, we zoomed into what does it look like on one Postgres. But for cross-tenant query, we actually may need to touch multiple Postgreses. One of the things is that there is a limit to how many partitions you can put in a single Postgres for reasons that I'll get to in the next slide. So the table, basically every shard has a separate set of partitions in a partition table. In order to enable cross-tenant queries, we also added table inheritance. We cannot really mix them, but we can add them next to each other. So if we have a partition table called events, we also have events base table, and inherited from that, a bunch of events foreign data tables. We use foreign data wrappers to point to partition tables elsewhere. When you run a query on that, the local node has to calculate a plan for the local set of partitions, and then you query remote nodes as if it was one table. The planning for the other sets of partitions is pushed down into the other nodes, which basically allows us to distribute the planning process and reduce the planner overhead from having, remember, I'm talking about millions of tenants, we're talking about millions of partitions. The planner does not deal with that well, so we actually had to distribute the planning phase. So, as I said, we needed dual structure, basically because Postgres does not handle well having a million partitions in a single table. I mentioned the query planner overhead. There is also catalog cache bloat. So a connection remembers catalog information, caches catalog information for every table and partition it ever saw. If you use a connection pool, as we do in the proxy, it means that over time it sees a lot of those, potentially millions. Over time, every one of your connections will see a lot of those, potentially millions, which will take over your entire memory. I found a thread from, I think, 2015, where Tom Lane was like, yeah, there used to be a limit on the size of catalog cache, but apparently nobody is ever going to need more than 5,000 tables, so we don't really need this limit. Yeah, this turned out to be a small challenge. In addition, it was recently discussed, I believe, in the mailing list, that there may be vacuum memory leak that affects large number of partitions. We managed to avoid that as well. Now, the thing is that we cannot mix inheritance and partitions, and also you cannot really, partitions themselves, tables themselves, you can have a partition that is pointing a foreign data wrapper that points to a different table, but not in the structure as we built it. So this was the best structure we could come up with under those limitations. The other thing that was really important for us is to not have us too involved in the query planner. We are aware that query planner is one of the more complex parts of Postgres. We do not, as a fairly small team with the expertise that we have, we did not want to go into the adventure of doing tons of query planner. Props to guys from Timescale, for example, who did decide to go into that adventure. This decision has been made after talking to people who have done it before. So with all this in mind, what happens when I do a cross-tenant query? Well, first of all, I can route it anywhere. It doesn't matter. Find the least loaded node and send it over there. It doesn't matter. It's going to touch all of them eventually. And then we rewrite it to do select from the to-do parent. This is the local partition table, union all, and select from the to-do base, which is the base table from which all the foreign data tables are inherited. So this gives us a simple structure. Of course, if the query is more complicated, it's basically the same thing. You duplicate the query, and you put a union all in the middle. One of the big advantages of just duplicating, and that's why we wanted the table inheritance, is that we didn't have to add n number of clauses to the query. We always needed just one, which made a lot easier. The columns required a bit of rewrite, because if you do things like select star and the table had dropped columns, then you need it to, the attribute numbers that we needed when doing a rewrite are not going to 100% match. So we needed to insert nulls for columns that used to exist but no longer do. We are doing that as well. And this works for all queries, no matter how complicated they get. Note that union all is safe here, because all those sets, it's different tenants on each one. All the data sets are always 100% distinct. And the last bit, this is still work in progress. It's not in production yet, but I wanted to share it because, again, it was one of the reasons our architecture looks the way it is. And this is the reason we had to So far, I didn't really talk about our storage layer, and I didn't explain why we wanted to separate compute from storage. This is the reason we had to separate compute from storage. What if you want to move a tenant? Why would you move a tenant? Well, sometimes the customer wants to move a tenant because they know that it's going to get big and they want to give it a big machine. Sometimes I want to move a tenant because I can see that it's starting to get noisy, maybe affecting other people on the same machine. It's better for me to move it to the side. No matter what, we do an update. And we basically update the location of the tenant in the metadata, intercept that, and then we start preparing for the move. And the first thing we do is offline vacuum freeze. Why do we do it? Well, our goal is to basically take the data from one tenant and put it somewhere else. Remember that every single row in every single one of the tables has transaction IDs. X in, min, X max, there is LSN something, there's a lot of IDs. They're not going to match. The X max over here is going to be totally invalid over there, or possibly valid but very confusing over there. It's going to be a disaster. So we need to not care about all those. The way to not care about all those is to make sure that they're all -2. And this is what vacuum freeze gives us. So we start by freezing. We basically freeze everything that is not involved in an ongoing transaction right now. Once we've done that, we detach the partitions. We update the metadata. So at this point, our gateway knows not to route anything anymore. We kill every ongoing transaction because we have not found a way to move them over live, and we need to start moving because the timer is ticking. In general, it's not a huge problem. We also run usually with very strict transaction timeouts in general. This is one of our architecture things. As other speakers have said, long transactions are not great for busy OLTP systems, which we aim to be. Once we've done all that, one more important bit, really important bit. We also have to store to the side the transaction ID where we started the freezing, the transaction ID when we are ready to start moving, and the entire write-ahead log in between. And the reason is that we will have to deal with all the mid-flight data on the other side, so we better store that. Okay, moved stuff over. What does it even mean? Well, first thing is we do reattach partition. You don't know what it is because this is syntax that we've added on our system. It's exactly like attach partition, except that we tell it that the storage already exists. So there's no need to actually start a new partition. You just metadata update to point to the data that already exists on our storage layer. We update a bunch of metadata on our own. And at this point, we're actually ready to start querying. And there are two scenarios. One is that you touch frozen rows. Frozen rows are fantastic. You can update them. They will get new transaction IDs. Those are not a problem. But what if someone tries to touch an unfrozen row? That would be a bit of a problem. We need to decide what to do with it. This is why we have the wall. It lets us know, was it something that actually got committed? Is it something that we killed and we have to roll back? What do we do with this one? Once we decide what to do, we can set the visibility and we can set all the IDs to their new values. So we now, this basically, doing this in 2 steps allows us to minimize the downtime involved in this movement, and we kind of allow things to happen opportunistically. Now, as you can imagine, it was freaking a lot of work to get this architecture implemented. We did a lot, and we're happy because it gives us back a lot. It's horrible if you do a lot of work and then you don't get any benefits out of it. We feel like the ROI here was actually really good. So first of all, we got all our goals done, right? The tenant data is isolated. We can take this and scale it to very large, potentially millions of tenants. Single query performance is fantastic. Especially good if you use pgvector, because you no longer have those. I don't know how many of you went to the talk from Jonathan Katz. PGVector indexes are large, and you basically have to scan all of them. You cannot really filter them in any meaningful way. You do kind of weird nearest neighbor navigation. But if you have many small ones, and you only query specific ones of them, then suddenly you don't query 100 million vectors that you need to somehow load into memory and spill to disk and figure out how to navigate. You query 1,000, you query 20,000. Those are very manageable. So this was a huge benefit. Cross-tenant reports are going to run. Try not to have too many of them. If you need too many of them, you're probably not going to enjoy Nile very much. It works, but it's a distributed query. It goes through many machines. If any of them are slow, it slows down everything. So it will work. Let's put it that way. It also allows us, because we have the separation all the way down to storage and all the information we need in the catalog and everything, it lets us do a lot of stuff on the tenant level. We can take a backup of a specific tenant. We can restore a specific tenant. If you tell me, hey, I'm invoking GDPR, right to be forgotten, please forget my tenant today, I can not just delete your tenant immediately and just get rid of the partitions. I can also go back and delete every single backup I ever took from this tenant. This is fantastic. It's usually really hard. You need to know, why is this tenant query slow for this tenant and not the other tenant? I have partition level statistics for every one of my tenants. I can investigate, I can change them if needed, I can create a new index for one of the tenants if needed. I have tons and tons of flexibility. I can, of course, move tenants to a very big machine if I need to. And this is all very cost effective. Because I can move tenants, it means that I can pack machines a lot more tightly than I otherwise would. Nothing is perfect. The partitioning structure means that you have to have tenant ID in every primary key in order for the partitioning to work. You'd think that this is not a big burden on anyone. I mean, you'd want it in any case. Anytime you have multiple tenants, you want to have efficient access passes to specific tenants. You would be wrong. There are millions of developers who use systems like Django or Laravel that make it extremely difficult to deal with composite primary keys. In fact, they insist on not having composite primary keys. It has been way more friction and more headache than I ever anticipated. From all the things I thought are going to be difficult and cause friction, I did not expect tenant ID in primary key to be one of them, but here we are. The other thing is obviously that cross-tenant performance is not where we want it to be. Part of it is just, yeah, it's a distributed query. The other part is that the way we do it, like the union all, the optimizer doesn't always make good decisions, partially because we hidden so much information from the optimizer. How could it possibly make really good decisions under those conditions? The moment you have to start doing any kind of interesting joins, it becomes actually pretty bad. So this is something that we want to try to improve and make a bit less hacky and figure out the right way to do it in the optimizer. If anyone is really good at query planning by any chance and would like a nice, interesting job, talk to me afterwards. And then there is some smaller stuff that may or may not matter yet. First of all, this is limited to 16 million tenants. Why is that? Well, table space OIDs are 32-bit, like every single ID in Postgres. 32 bit. We took the first 8-bit, I believe, and we used those in order to support 55 regions. The rest limits us to 16 million tenants. So we think it's enough, but we'll see. Because we use the tenant ID in the partition name, even though we minimize it as much as we can, we are encoding it in some smart way, we still have slightly shorter space for table names than normal Postgres. And then when you create a tenant, you actually have to go and add all those partitions. When you delete a tenant, you have to remove all the partitions. God forbid if you go in and truncate the entire tenant table, we have a lot of DDLs to do. We could do it a lot better. We could do it opportunistically. Maybe you're not going to need all those partitions for every table. This also deals with the catalog cache, which is another pain point. So we can do it a lot better, but right now this is fairly slow, depending, of course, on how many tables you happen to have. Stuff we want to do in the future. We have stuff that we want to do in Postgres, like just better way to put the whole inheritance table and union all and partitions. It feels like a hack. We want to find a better way to do it. Something that we thought that will be a good idea, just ridiculous amounts of work. We thought about lightweight partitions as table spaces. Imagine a world where every table, instead of having one table space, you had a list of table spaces. And you would query it as if it's a single table space, but the storage layer would get the ID of the tenant and would only query the correct table space for the tenant. So we actually push the filtering, the partitioning pruning, all the way down into the storage layer. This seems like it, again, tons of work. How will the vacuum process work in that scenario? How will anything work? How will transactions work, for that matter? So it's something that we're still trying to figure out, but we think it can basically take a lot of load off the catalog and off the query planner and make things faster and cleaner. Something else that I was told would get a lot of pushback, but I'm going to say it anyway. The fact that we have to pre-create all those partitions, it's kind of annoying. And we are not the only people in the world who have to pre-create a lot of partitions. I mean, everyone who partitions by time has to create new partitions on a weekly, daily, monthly, hourly, whatever basis. There are solutions like Partman, but it would be possible for Postgres to opportunistically create partitions if you do an insert into a table with a range identifiers that does not yet but could exist. So this is something we think it's nice. I was told that maybe not everyone in the community will agree that mixing DML and DDL is going to be the best idea. Something less controversial. We were missing hooks. Everyone is missing hooks. Everyone who ever wrote an extension is missing some hooks. The ones we're missing is, first of all, being able to hook into the query planner before we lose the names of the tables and have to figure out the attributes and the columns that were deleted and all that. That was kind of annoying. The second more important one, storage manager is not extensible. You cannot easily replace md.c with anything else. We're not the only ones who need to do it, obviously. OrioleDB people needed to do it. Aurora probably had to do it. We used patches that we got from Neon. Thanks God they contributed them. It will be nice to actually get this into Postgres. On our side, we have a lot of stuff we know we can do with this architecture we have not done yet, and also stuff that we know will get us to 100% Postgres compatibility, but we have not done yet. So for me personally, change data capture is probably the cool things that we're missing. We could do change data capture stream for each tenant individually, so you can subscribe to stuff from individual tenants. It would be really cool. For just summing stuff up, Postgres scales really, really well. Don't get into this adventure unless you actually have to. And then if you have multi-tenant workload, you can shard it by tenant. That is the cool bit that started everything. And then if you do partitioning by tenant and you decouple storage and compute, you get a lot of benefits. I wouldn't say for free because it was a lot of work, but you get all these benefits. And then if you actually want to discuss it more, tell me that we're doing something crazy, make suggestions, ask questions. I would, as you can see, I love talking about this.
Now it's time for questions. He was first.
Thanks. Yeah, so I have a question about the Nile gateway. I think in one of the slides you show that it can route a query to the correct server,
yes.
right, the tenant. But it looks like it requires either the user or the application to set the tenant ID beforehand, right? So I'm just curious, does the gateway has any smarts to say, maybe cache where the location of the
yeah, so
like
first
the
of all,
tenant is,
it
and then
does
it can automatically route, like maybe extract or parse the query to.
So yeah, it does cache. So after you set the tenant ID once, everything you do on the same session would go to the same place with no extra. You'd never have to say it again. So it is sticky. So you have this benefit. We could be smarter and try to pull information out of the query, and if you have a workload. Queries get very complicated, and we did not want to do a lot of parsing in the gateway itself. It's much easier. We do all our parsing in the extension where we can have basically Postgres create the parse tree for us instead of having to figure it out ourselves.
Just a related question is like when you move a tenant, right? So let's say the applications sets the tenant ID to server 1 and then sends the queries over. But then actually that tenant is in the middle of moving to end the server. So what happens? Does the gateway queue up?
Yeah, so right now we queue up. We don't until so we have timeouts. So it queues up for a bit. It survives the timeout. It usually survives the timeout. So it looks like a spike and a small delay. It's I don't know, hundreds of milliseconds kind of delay, and then it goes to the new location. We don't know that queuing is the behaviors that everyone wants. Maybe they want it to fail fast and retry. We will find out. That's the exciting thing about building new systems. You discover how people want to use them.
I've been already quite exposed to Nile, been reading a lot, following a lot, and I have like maybe a dozen questions or more. So you did a great job with your talk. So I'm gonna pick one. And all the architecture is quite interesting to me. Now, have you considered, and probably this comes late, but have you considered following an architecture more similar to DynamoDB's? I say this because actually I gave a talk at a past conference. Slides are online if you want to. That is called "Can Postgres Scale Like DynamoDB?" and where I kind of design an hypothetical architecture of how to partition. Some ways it's similar to this, using multi-levels partitioning with foreign data wrappers, pointing to tables which are partitioned on different nodes. Very similar concepts, but I think there could be some interesting lessons learned there.
So I'll have to read or watch your talk or read the paper if you publish one. We have looked at several architectures to get inspired. So DynamoDB has been one. Obviously, all the Aurora papers, everything ever published by Snowflake, in which it was not quite enough. What else? I think those were the major sources of inspiration. So yeah, this was definitely DynamoDB inspired and Aurora inspired. And if you have more ideas, then maybe we can make it even better.
Yeah, with pleasure.
Any more questions? Okay.
So I'm actually going to piggyback off of his question because I also know some of the backstory here. So my understanding is when you started down this path, it wasn't like you were trying to make a Postgres specific thing, right, for tenants. You're trying to make a database service to do massive tenant management. So but at some point you settled on Postgres, and like it seemed like that's a feature set that you wanted, right? Whereas I would look at like a Dynamo and I would think like, wow, I'm going to lose like all of these features. Like, was there ever a point where you were like, we really kind of do need a lot of these features that we get from a relational database and we would get with Postgres, which would steer you away from the Dynamo stuff?
Pretty much. So when we started, we seriously considered MongoDB as the basis. Sorry, I know that there's a lot of anti-Mongo people here, but it was something we were not at the point in time quite aware of a lot of the cons of Postgres, so it was maybe a bit of a lucky choice. But the thing we really bet on was two things. One, the future of relational databases in general. We thought that relational as a theoretical concept is a better basis for building applications than every other concept. Like you can patch stuff, you can put DynamoDB where needed, you can put some Redis in places, but at the end of the day, you want to have a relational data architecture at the basis of your application. So this is something that we really believe in. The other thing we bet on is, quite honestly, the Postgres community. We looked in a lot of places, we saw how vibrant it is, we saw all the activity, all the conversations, all the discussions, how fast people jumped in to help when we had questions, when we wanted to chat out, compare ideas, exactly what we are all doing this last couple of days here right now. We love the extensibility, the extension, infrastructure, and all the cool stuff that people do as extensions. So for us, it was really a bet on, yeah, I guess 3 things: relational databases, Postgres community, and Postgres extensions as part of this community.
Just a very, very quick comment piggyback on what you were saying.
What's up with you guys?
And it's basically that you're absolutely right. DynamoDB makes a lot of compromises and exposes a very small subset of what Postgres can do as a relational database. Now, funny part is that, and there's no official confirmation of this, but DynamoDB is built on top of a relational database.
Ooh.
I call DynamoDB an HTTP server on top of a relational database with a lot of quotes before and after.
We can take one more question.
Yeah, there's the guy waiting patiently all the way in the back. Wait for the microphone so you'll get recorded.
Okay, have you considered building this on top of separate databases for every tenant, creating a separate database that would resolve some of the issues with difficulties with multiple partitions?
We have, and we may still end up doing that. So there is definitely pros, as we discussed, there is pros and cons to each. And we think that there is different situations where you may benefit from each one versus the other. And we are seriously considering whether it's possible for us to actually have both models and let people choose.